So last time we talked about electric field and ended with field due to continuous charge distribution. On Friday, got some more practical fields and with a ring-shaped charge. And if you didn't get a chance to, if you didn't have enough time to finish all those questions on Friday, try them out yourself. Feel free to bring those questions to office hours. Yeah. But we are going to move on. Well, let me just say this. If you look at the slides, there are always questions that we don't have time to go over in class. So do take a look at those. Don't assume that just because we didn't go over them, they're not important. Do go over those. There are some useful ones there about continuous charge distributions. But we have a lot of material to cover. So I'm going to move on, but feel free to bring questions to office hours. All right, so today I'm going to talk briefly about dipoles, then about electric flux. And hopefully just a little bit about Gauss's law. All right. So dipoles we've already met. It's basically you have two charges, one positive and one negative. But strictly speaking, in the definition of dipoles, these have to have the same magnitude. So if this is plus q, this is minus q, right? So dipoles are important because they often arise. They arise in lots of different circumstances, but in molecules they happen a lot. So I'll just represent them as two charges, one plus q, one minus q, separated by a distance d. This is a dipole, and it turns out to be convenient to describe something called a dipole moment. To this dipole. Somewhat unfortunately, the symbol is P. Yeah, so you have dipole moment P, it's a vector. The magnitude of this vector is q times d. Right, so it's just the magnitude of one of the charges times the distance between the two charges. So that's the magnitude of the dipole moment. But it's a vector, so it has to have a direction. And the convention chosen there is that the direction is from the negative to the positive. Questions so far? Yes, Harry.
So what does it mean by a dipole moment?
It contains some information about the distribution of charge. And you might say, why do we define it this way? If you go further on into electrodynamics, what you will find is there is a way of describing a charge distribution, and you basically get more and more information with each bit of the description. So like if you have some arbitrary charge distribution, okay, you have some arbitrary charge distribution. The first bit of information is what is the total amount of charge there. So that would be the monopole, right? It's as if you treated all of it as a single point, right? And this is some information you can get from far away. But then you want a bit more information about, because you know it's not actually a point, it's distributed somewhat. The next bit of information that comes out is the dipole moment. And then you can construct, this is a vector, and then you can construct a tensor called the quadrupole moment, and it goes on and on. And so as you get more and more information, you know more about how this charge is distributed throughout space. Pretty.
So this is a vector.
Yes.
We can only
calculate its magnitude using two scalars, and then we assign
Direction.
afterwards. Why don't we just use R, like R vector pointing from negative to positive?
Yeah, no, I mean, like if you define this D vector to be pointing from negative to positive, yeah, then that would work. Yeah. Other questions? Oh, Harry, yeah.
So is that Q the single charge value or?
Yes, yeah, just a single charge value. Yeah. Oh, okay. So, all right, so we have this dipole and this dipole moment. So now, why are we interested in dipoles? One reason is how they behave when you put them in a field. So supposing we have an external field, E, and then I put this dipole in this. Actually, I think I have a question on this. Let's see. Okay, no, I don't. So, yeah, so supposing I have a dipole like this, what do you think will happen to this dipole? Either.
There'll be a torque exerted because the positive terminal of the dipole will create the force towards the right, and the negative will create the force towards the left.
That's right. So what Aiden said is that there would be a torque, and as a result, the dipole would turn, right? And we can see that because if we look at the force on this positive charge, the force on the positive charge would be this way, right? And the force on the negative charge, remember F equals EQ. So if you have a negative charge, the force will be in the opposite direction to the electric field. So the force would be this way. Now, assuming this is a nice constant field, and we know by the definition of the dipole that the magnitudes of the charges are the same, and these forces have the same magnitude, but they're pointed in opposite directions. There is no net force, but there is this rotational, there is this torque. And so what will happen? This dipole will rotate to like this. Question, Simon?
And so basically at equilibrium, these the dipoles will orient themselves along the field.
Exactly, yes. So part of the reason why we define the dipole moment this way is that, so remember, the dipole moment goes from the negative to the positive. As Samuel said, what you can see is that, oh, okay, it wants to rotate to become like this. And so the dipole moment aligns with the external field. Questions? Yes, Fred.
Wait, so by a line, do you mean just it would be horizontal?
I mean, it will become parallel to the field. So in this case, because the field is horizontal, the dipole moment will also become horizontal. If the field had been going like this, then it would rotate too.
So it won't keep rotating.
Okay, good question. So if I started out in this position, right, what will happen? It will rotate like this. It will come to this point. At this point, there's no more torque. But if it's just an ideal dipole sitting by itself, it would have built up some kinetic energy. So it will overshoot, but then it will feel a torque the other way. So then it will just oscillate back and forth. In reality, though, these dipoles usually occur in some bigger solid or liquid or something. So as they rotate, they start losing energy by jostling with other molecules. And so eventually it'll die down and they'll all align. William.
Is the force from the electric field conservative?
Yes, it is. Good question. Other questions? Okay. What do I want to say? So yeah, so this was. So yes, so if you place a dipole in an external field and it's free to rotate, it will rotate to align with the external field. Align the dipole moment with the external field. Now, you might ask, how much is the torque? So we could calculate the torque. I mean, we know the force and we know the distance from the center. So we could calculate the torque about the center. And if we just wanted the magnitude, we could say, oh, okay, it's RF sine theta just draw that dipole a little bit bigger. And so we have force. This is the central axis. We know that this distance is d over 2. The force is here, and then the angle. So remember, it's r cross f. So r would be pointing like this. So this angle would be theta. Yeah. So which would be the same as this angle. All right. So we said, okay, R is d over 2. And the force, what can I put for the force? EQ, exactly. It's just a charge in an electric field. So I put EQ sine theta. And this is the torque due to just one of the forces, right? And so I would double it because the other charge also feels a torque. And so we get that the total magnitude of the torque is dQe sine theta. Well, we know what dQ is. Sorry, maybe I shouldn't call it dQ, that's confusing. QD. Yeah, let me put it this way. EQD. Okay. We know what QD is. QD is the dipole moment. Okay. So it turns out that you can calculate the torque just by doing P cross E. That is the torque on a dipole if you place it in an external field. We can, question here.
If you have your dipole like parallel to the field, but say the negative was on the right and the positive was on the left, like in this example, how would you know which way would rotate, or would it not matter?
So Zach's question is, what if I have the dipole exactly in the opposite direction? So the dipole moment is like this. So if it's exactly opposite, it is in equilibrium, but it's an unstable equilibrium, right? So if you were able to keep it perfectly like this, then it would just stay like that. There'd be no force. But the slightest disturbance would make it rotate. And then whichever way the disturbance was, that way it would be. Wait, William.
It's P cross E.
We can check that that gives the correct direction. So right now we have P this way, and we have, I guess, E this way. So if I do P cross E, and we can see that that corresponds to like R cross F. Other questions? Okay. Now, William asked a nice thing earlier about is the electrostatic force conservative, and it is. And we'll, in fact, talk more next week, I think, about the potential energy associated with that in the general case. But even in this particular case of a dipole in an external field, there is a potential energy that you can associate with it. So let me put that here. So you get U is equal to minus P dot. Yeah, which I can expand as minus magnitude of P, magnitude of E, cosine theta. Now, what do we know about a system with a potential energy? If you let a system go, what will it try to do with its potential energy? It will try to, in generally, systems try to increase, decrease, decrease their potential energy, right? Usually the most stable configuration for the system is the lowest potential energy. So here we can see that, when theta is 0, right? What do we get? We get cosine of 0 is 1, and so you get minus PE. That is the smallest value that this can take. The lowest value can take, the most negative value that it can take. Okay. You can see that when theta is 90 degrees, you get 0. When theta is 180 degrees, you get plus PE, which is the highest value that it takes. Right? So it tells us, okay, the most unstable is the anti-parallel position, and there's then it decreases as you turn to the parallel position. Any questions? Yes.
If theta was 90 degrees, wouldn't it be going like this? So
Yep.
the most force?
That would be the most force, but not the most potential energy. Yeah. Yes.
When did you say the highest potential energy is?
The highest potential energy, which is the bad thing, so to speak, is when theta is 180 degrees. So when it's anti-parallel, because then you get -1 here, and minus gives you plus PE. So it's the most positive. Okay, so why are dipoles interesting and relevant? Partly, as I was saying to Harry, it's one of the ways we get information about a charge distribution. But I mentioned also that they arise when dealing with molecules. In particular, they arise when dealing with water. So if you look at a water molecule, which is H2O, it's a very rough schematic. And we know that they are covalent bonds between oxygen and hydrogen. In fact, they're polar covalent bonds. The electron is not shared equally, but spends a bit more time near the oxygen, a little less time near the hydrogen. And so the hydrogen has an effective small charge plus delta over here. It's not an ionic bond, so it doesn't completely rob the electron from the hydrogen, but the electron spends less time near the hydrogen, so it's effectively a little bit positive. Same thing over here, and the oxygen here is a little bit more negative. Now you might say, well, wait, this isn't a dipole, right? I mean, there are three things, and they're not equal charges exactly. What's going on? Any ideas on how we can treat this? Yes, sir.
You combine the vector.
Exactly. So this is where the fact that the dipole moment is a vector comes in handy. So we can break this up into two dipoles. So we say that, oh, okay, there is one this way, negative positive, and there's another one this way, right? So we break up this -2 delta into one minus delta, another minus delta. So one dipole this way, one dipole this way, and as Christine said, they are vectors, we can add them. And so we get the total dipole moment is like this. Now, the fact that we have these slight charges on oxygen and hydrogen leads to a number of remarkable facts. This is what leads to hydrogen bonding. It leads to the fact that ice is less dense than water, right? Because when it crystallizes, the most stable configuration, you can't have the molecules just higgledy-piggledy. You want them, they would prefer to be arranged so that like this hydrogen is near the oxygen of the next molecule. Like this, because this will have a -2 delta. So there's an electrostatic attraction here. That's basically what the hydrogen bonding is. And this repeats. And so that they have to have a certain minimum space between them. And that's since they have to move a little bit apart to create that space, ice becomes less dense than water, and it floats. And of course, this has huge implications for life on Earth, because if ice wasn't less dense than water, what would happen in the winter? Most materials, when they solidify, get more dense. So if water was like that, in the winter, the water would freeze, the top layer would freeze, and then sink. Then the next layer would freeze and sink. And if you had a long and cold enough winter, the entire pond or lake would freeze. Right? And so unless you had life forms that could survive being freezed and then thawed, frozen and thawed, then, well, no, every winter things would just die off. Right? But instead, what happens? Ice is less dense, so it floats, stays on the surface, forms an insulating layer, and protects the water underneath. The water becomes cold, but doesn't freeze solid. And so you have life that can survive over the winter inside ponds. They just, go to low metabolism and the state, they survive through the winter. So yeah, hugely important to life on Earth. Questions? Okay, let me ask just a couple more questions about dipoles. Go ahead, pull your clickers out. Okay. Simple one first. Let's be quick on this. So mostly for C is correct. If we look at the charge, it's 2 nanocoulombs. Look at the distance, it's 2 millimeters. So we multiply them, so 2 times 2 is 4. Then it's just the powers of 10. So this is 10 to the minus 9 times 10 to the minus 3 is 10 to the minus 12, which is pico, exactly. And so yeah, we have 4 picocoulomb meters. All right. Yes, let's try this. Okay, so sort of split between B and C. The C crowd, be careful though. Don't assume that the stuff that's presented on a plate to you is necessarily what you want. So what's the formula that we're using? Just call it out. Minus PE cosine theta. And minus P dot E. So minus PE cosine theta. And how do we find theta? What is theta? Theta is the angle between
the field and between the dipole moment and the life field.
Between the dipole moment and the field, right? If you're taking a dot product between P and E, it's the angle between the dipole moment, which points like this, and the field, which points like this, which is just 30 degrees. Okay? So the rest of it I'm sure you got right. Just be careful with the angles. Okay, one last dipole thing. So we've been talking about a dipole in uniform field. What if I put a dipole in a non-uniform field? Okay. Go ahead and, question, yeah.
No.
Oh, you were about to, go ahead and discuss. Oh, question.
Looks like it's
Yeah, I mean, don't worry too much about its position as such. Just think about how the field is behaving. Yeah, like where's the field strong? Where's the weak? Okay, mostly for B. B is correct. Anyone want to defend their reason? Yes.
The electric field is stronger towards the bottom.
Yes.
You see the lines get closer together.
Yes.
So the dipoles are towards the stronger and more aligned fields.
Skipping a few steps there. Kevin.
You know that the dipole moment moves from it goes in the direction of the negative charge to the positive charge.
Yes.
And the negative charge is closer to the stronger field. So
Yes.
Coulomb's law, the force will be greater.
So yes, so putting those two things together. So if we think of this as a negative charge and a positive charge, which one is on top, the positive or negative? The positive one is on top and the negative one is on the bottom. Which one sees the stronger field, the positive or the negative? The negative sees the stronger field. Which direction is the force that the negative charge will experience? Downward, against the direction of the field. So they both feel forces, but now because it's a non-uniform field, the positive charge feels a force upward, but it's a weaker upward force. The bottom charge feels a force downward, and it's a stronger downward force because it's in a stronger field. And so the force that wins is the downward one, and it will move that way. Yes, Julie.
So the field lines are parallel with the
No, the field lines are parallel. What would that tell you about the field strength? They're the same, and so the forces would cancel. If it started at rest, it would stay at rest. Freddie.
So if I have an ununiform field that's like this shape.
Yeah.
And there's a point where it can be stable, like.
Oh, yeah, you
Would
could
I
trap,
say
you could trap it between, well, here, in this case, it's moving towards stronger field, right? Because it's aligned in this way. So yeah, it would, you could trap it in the middle. Like if you had field lines that went like this, you could trap it in the middle where the field is strongest.
Yeah.
The same. Okay. So yeah, we'll see this again, in fact, when we come to magnetic materials, and that this sort of, because there are not only electric dipoles, there are magnetic dipoles, and that will explain why different magnetic materials react in different ways. Okay, spent a lot of time on this, but one last thing. Two last things. One other way that we could explain this, other than force, is we could use potential energy. Right now, what is the angle between the field and the dipole moment? Zero. They're pointing in the same direction, right? So we could say, okay, theta is 0, and so U becomes minus PE cosine 0. The cosine of 0 is 1. So this is just minus PE. Now the molecule, its properties are fixed, so it can't change its dipole moment. So P is fixed, but it can move to change the electric field that it sees. And here, if it wants to decrease its potential energy, it wants it to become more negative, it will move to a stronger field, which is done. Questions?
I'm still a little bit confused about that kind of situation, like when the dipole can rotate, the P will change, right?
No, the magnitude of P will not change, right? Because I mean, it rotates assuming a fixed distance between them.
Yeah, but if we want to use that equation in vector form, should we like have different result?
Say again.
If we want to use that equation of vector form,
Yeah.
the result will be.
Result for what?
Oh, I got you.
Okay.
Sorry.
So in uniform fields, will a dipole moment be accelerating or decelerating? Should that be the case? Because in the uniform field,
Yeah.
Okay. First of all, in the uniform field, does the dipole movement move in like constant velocity?
If you give it a constant velocity, then yes, it will continue with constant velocity.
So in the ununiform case,
If it was initially moving, yeah, then it would accelerate one way or the other. Yeah. And if you had a case,
The sides of the sphere, there's gonna be like an infinite number of vectors covering the sphere and.
right, exactly, yes. So what you would do is you would chop up the area of the sphere into tiny, tiny pieces, each one small enough that it can be considered flat. And then, yeah, you would have a small vector perpendicular to that surface, then the next one over, small one. So sort of like the situation here. Here, the area vector will be pointing like this. Here, the area vector will be pointing like this. Exactly. So it's always going to be perpendicular to the surface. Yes.
Could there be like holes inside the volume being enclosed, like something akin to a shell with that's
Shall we? Oh, I see. We would treat that as like building it up out of several cases, so that we would treat that as like one sphere inside another, basically. Yeah. So The surfaces that we are considering are infinitely thin. And anything thicker you can build out of those. Angela.
So if a sphere has like infinite area vectors,
Uh-huh.
how do you choose which one to use when you're integrating?
Oh, I mean, you end up using all of them. I'll explain how that would work. So yeah, just. Oops. So yeah, if you had a sphere, if we had a point charge right in the center, then the field lines would be going outward in all directions. And so over here, if you looked at the DA, use a different color if I have one. So let's say we're using white for the electric field, and then DA would be like that. DA over here would be like this. DA over here would be like this. And so what you do when you do the integral is, well, basically for each DA, you are looking at what the electric field is at that DA. You are doing the dot product, and you get a scalar quantity. And then the integral is just adding up all the contributions all over the sphere. And there was a question, what is the circle on the integral symbol? We use that if you're dealing with a closed surface. So that's all it indicates. So because if you notice the definition of flux, there is no circle because the surface that you're calculating a flux through doesn't have to be closed, right? Surface could be closed or not closed. You can define flux either way. But if you deal with a closed surface, we get a nice result, which is Gauss's law. And so that's why the circle appears. 1 second. So in this case, what would we do if we were calculating the flux? If the charge is right here in the center, well, we know that the field would be, in general, this. But let's say that this has a radius capital R. So you could specialize this to R cubed, this R vector, dotted with dA. But the dot product would give me magnitude of R, magnitude of dA, times cosine of the angle between them. What is the angle between the electric field and the dA vector? 0, because they're both parallel, right? No matter where we go, they're both parallel. So in this case, we would end up with one of the r's cancels. So you have k cubed r squared dA cosine of 0, which is 1. And we're doing an integral, so we can pull out the constants. So pull out the k, pull out the q, pull out the r, pull out the cosine of 0. And so we end up with kq over r squared times integral dA. But we're just integrating all these little bits of area over the entire surface. And so we just get the surface area of the sphere. What is the surface area of the sphere? 4 pi r squared. Let me just move that here. So we get k cubed over r squared times 4 pi r squared. R squareds cancel out. I get 4 pi k cubed. And we haven't really talked about it, but hopefully you've seen in your reading Coulomb constant K is often written as 1 over 4 pi epsilon naught. This is just convention. Okay, there's nothing really special. And so if it's written that way, then the 4 pi's cancel out and you get Q over epsilon. Sorry, I know I wrote this in slightly confusing presentation. Questions? Yes.
So epsilon is actually a constant.
Epsilon naught is a constant. Yes.
Do we need to know the exact value of it?
It'll be on the formula. Any other questions? Okay, I'll just end with the statement of Gauss's law since we came this far. So Gauss's law basically says if you have a closed surface, right, which encloses some volume, and you calculate the flux through that closed surface. So that's why I'm putting the circle here, right? So this is flux through a closed surface. And Gauss's law says that this is going to be equal to the charge enclosed over epsilon naught. This is electric flux. I'm putting GS here for Gaussian surface. Now, you might say, oh, okay, well, that's indeed what we saw. We calculated the flux through the sphere with the point charge inside, and we got Q over epsilon naught. But what's remarkable is this. We were only able to do this integral because the charge was right at the center. Right? If it was moved off to one side, then I couldn't make the simplification of the field being constant in magnitude. Right? The field would not be constant in magnitude. It would be stronger in some places and weaker in others. And the angles would change too. It wouldn't be 0 degrees everywhere. But what Gauss's law says is that even if you did that, as long as this charge was remaining inside, no matter where you moved it inside, the total integral would stay the same. Even if it became complicated to calculate using this, Gauss's law basically guarantees that as long as it's inside, the charge enclosed stays the same, the total flux will stay the same. All right, that's it. Thank you for your patience. Those of you in lab starts this week, and you must do the pre-lab before coming to lab.